Good morning, anatomy students. Since I can't be there with you today, I've made a video of our notes so that we can continue learning even while I'm gone. So today we'll be going over Chapter 2, starting with basic chemistry. And our objective for this section is to be able to distinguish between the atom, element, molecule, and compound. And this should be familiar to you from your work on Friday with your concept map. So our notes show that matter is anything that takes up space and has mass, and hopefully we remember that from physical science or from chemistry, and that there are 3 states of matter: solid, liquid, and gas. So make sure that you record that in your notes, just in case you didn't remember the 3 major states of matter. We won't get into other types not typically found on Earth. Elements. The most important elements for you to remember for anatomy are the 4 elements that make up over 90% of the human body, and that's carbon, nitrogen, oxygen, and hydrogen. And in letter B it says they're represented by a symbol containing 1 or 2 letters. This is very familiar to you with the periodic table. So this chart does a good job of showing us the elements that will be important to us as we move forward. At the top, we see hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. And when we start talking about protein building and the difference between carbohydrates and lipid structure, we will need this information. Down at the bottom, you're going to see sodium, magnesium, chlorine, potassium, and calcium. And these elements are going to be important for us to know about as we start learning about muscle contraction and nerve impulses, learning how they work. You'll need to remember about those elements. All right, now atoms are the smallest unit of an element that have the chemical and physical properties of that element. So again, back to Chem 1. This is pretty standard, not surprising. And we do need to be reminded that there are subatomic particles, including protons, neutrons, and electrons, and that protons have that positive charge, neutrons no charge, hence the word neutral, neutron, and then electrons have a negative charge. And there's a certain way that electrons can be arranged. And here we have a nice picture. Notice that in the first shell, we only have 2 electrons present, and then in outer shell, this one, we have 1, 2, 3, 4 valence electrons, but you can have up to 8 in that next level if it were a different atom or if it were an ion with a 4 negative charge. Okay, so the atomic number is the number of protons in the nucleus. That's what identifies the element, and it's what you're going to be looking for on the periodic table if you take a look. And then the mass number is going to be the number of protons plus neutrons. And again, very familiar from Chem 1 or even physical science freshman year. That number is not found on the periodic table. The number that you find on the periodic table is going to be an average of all the isotopes found in nature. So it's not going to be a whole number. A mass number is a whole number. And just really quickly, let's take some time to review. What I would like you to do is press pause and answer these questions, and then in just a moment, unpause the video and we'll go over the answers together. All right, welcome back. I hope you've taken the time to answer these questions already, and now we'll go over our answers together. So our first question, the smallest unit of matter is the atom. And an element is any substance that contains one type of atom. The positively charged particles in the nucleus of an atom are protons. The atomic mass of a proton is 1 AMU. That stands for atomic mass unit, but if you just wrote the number 1, that's okay too. Which subatomic particles are found in the nucleus? Protons and neutrons. The number of protons is called the atomic number. The proton is the subatomic particle that determines the identity of an atom. And electrons determine the chemical activity. Now, I didn't mention that, but I did mention earlier the word valence electrons. Those are those outermost electrons when you're looking at an element. And when you think about it, if 2 atoms bump into each other in space, what's going to come in contact? not the nucleus. That's in the very center. The thing that's going to come in contact with one another are those outermost valence electrons. So that is what's going to determine its chemical activity. All right, now the mole. I know you may or may not have talked too much about the mole in chemistry. I hope you did, and I hope you remember Avogadro's number of 6.02 times 10 to the 23rd. A mole is a quantity. It's a number of atoms. So it is 6.02 times 10 to the 23rd, which is a lot, but it is based on the number of atoms and exactly 12 grams of a carbon-12 isotope. So that's where the number comes from. It is a quantity, just like 12 is a dozen. 6.02 times 10 to the 23rd is a mole. All right, and I mentioned isotopes a few times now. They're variations of one type of atom that differ in the number of neutrons, but the number of protons does not change. So we talked about how the identifying feature of an element is that number of protons, so that's not going to change. Down at the bottom, I think C and D are the most important for you to know because they are how it relates to our study of anatomy in the body. Letter C says low levels of radiation can be used as tracers, x-rays, and mammograms. Those are just some examples. And high levels of radiation can be harmful to cells but are also useful, such as for cancer treatment or sterilizing medical and dental equipment. So those are the two reasons that we might want to learn about isotopes and or radiation. All right, molecules and compounds. So here's a new objective up at the top, things you need to learn. We have to be able to describe atomic structure, types of chemical bonds, and types of chemical reactions. So down at the bottom we have two fairly simple definitions. Molecules form when atoms bond to each other by covalent bonds. Compounds form when atoms of different elements bond. So one of the types of bonds that you need to know about is an ionic bond, which should be review. It's where we have the attraction of a positive and negative ion, and they're held together by that attraction. So here is an image that shows that. The sodium atom, when it comes near the chlorine atom, the chlorine is a lot more electronegative and it pulls more strongly on that electron, and so sodium will give away its electron and chlorine will gain it. And you'll notice here, chlorine now has 8 valence electrons, which is the most stable configuration, and now sodium also has 8 valence electrons. Once it peeled off that outer shell, there's a stable, full electron shell underneath. That's why it makes it more stable. Covalent bonds are when an atom, instead of sort of stealing an electron from another, will share it. And there's a couple different kinds. We have single, double, or triple bonds. And you can have polar and nonpolar covalent bonds. Polar would be when there's an unequal sharing of electrons. And I already mentioned electronegativity. So the more electronegative atom, that means it's going to pull more on that atom, more on the electrons, and they're going to shift to that side. So that's what a polar covalent bond is. And then a nonpolar covalent bond is when they share equally. And so here's some examples of covalent bonding. We have an oxygen and 2 hydrogens, and they bond together to form water. So you see the 2 shared electrons right here and right here. Again, oxygen has 2 in that first energy level, and now it has 1, 2, 3, 4, 5, 6, 7, 8. So oxygen is stable, hydrogen is stable because its outermost shell is full with 2. And here is nitrogen, a nitrogen molecule where they're bonded to one another, an N2 molecule, which is actually most of the air that you're breathing in right now, has a triple bond, 1, 2, 3, is how they fulfill that requirement of wanting 8 electrons in their outermost shell. All right, let's take a moment to practice. Please pause the video and then we'll go over the answers together. All right, welcome back. Let's go over our answers to our practice questions. First, we have atoms bonded together to form a chemical unit are called molecules. A molecule made of 2 or more different atoms bonded together is called a compound. Going back to number 1, one thing I wanted to mention is we said the word molecules is for covalent bonding. If we had a bond that was ionic, you would actually call it a formula unit. So if you see that written down, that's where that came from. Number 3, an atom or group of atoms that's charged is called an ion. An ion is an atom or molecule that has a charge due to uneven number of protons and electrons. And you'll see here I wrote proton P plus because it's a positive charge, and I wrote E minus because electrons are negatively charged. Number 5, a bond created from the attraction between positively and negatively charged ions is an ionic bond. If they're sharing, it's a covalent bond. If 2 pairs are shared, it's a double bond. And when one atom has a stronger attraction, it's called a polar covalent bond. Okay, the next objective that we need to talk about today is we're going to differentiate among acids, bases, and salts, and then discuss the characteristics of the pH scale. All right, now, I think it's been 11 minutes, and I think you've probably listened to my voice enough for now. So I have a very cute video clip that will walk you through the discussion of water and why it's such an important biological molecule. So I am going to turn it over to Crash Course, and they're going to explain to you the importance of water in biological molecules, and then we'll come back together to talk about acids and bases.
Hello there. Here at Crash Course HQ, we like to start out each day with a nice, healthy dose of water in all its 3 forms. It is the only substance on all of our planet Earth that occurs naturally in solid, liquid, and gas forms. And to celebrate this magical bond between 2 hydrogen atoms and 1 oxygen atom, here today we are going to be celebrating the wonderful life-sustaining properties of water. But we're going to do it slightly more clothed. Much better. When we left off here at the biology crash course, we were talking about life, and the rather important fact that all life as we know it is dependent upon there being water around. Scientists and astronomers are always looking out into the universe, trying to figure out whether there is life elsewhere, because, you know, that is kind of the most important question that we have right now. They're always getting really excited when they find water someplace, particularly liquid water. And this is one reason why I and so many other people geeked out so hard last December when Mars's 7-year-old rover Opportunity found a 20-inch long vein of gypsum that was almost certainly deposited by long-term liquid water on the surface of Mars. And this was probably billions of years ago, and so it's going to be hard to tell whether or not the water that was there resulted in some life. But maybe we can figure that out, and that would be really exciting. But why? Why do we think that water is necessary for life? Why does water on other planets get us so freaking excited? So let's start out by investigating some of the amazing properties of water. In order to do that, we're going to have to start out with this. The world's most popular molecule, or at least the world's most memorized molecule. We all know about it. Good old H2O. 2 hydrogens, 1 oxygen. The hydrogens each sharing an electron with oxygen in what we call a covalent bond. So as you can see, I've drawn my water molecule in a particular way, and this is actually the way that it appears. It is V-shaped. Because this big ol' oxygen atom is a little bit more greedy for electrons, it has a slight negative charge, whereas this area here with the hydrogen atoms has a slight positive charge. Thanks to this polarity, all water molecules are attracted to one another. So much so that they actually stick together, and these are called hydrogen bonds, and we talked about them last time. But essentially what happens is that the positive pole around those hydrogen atoms bonds to the negative pole around the oxygen atoms of a different water molecule, and it's a weak bond. But look! They're bonding. Seriously, I cannot overstate the importance of this hydrogen bond. So when your teacher asks you, what's important about water? Start out with hydrogen bonds, and you should put it in all caps and maybe some sparkles around it. One of the cool properties that results from these hydrogen bonds is a high cohesion for water, which results in high surface tension. Cohesion is the attraction between two like things, like attraction between one molecule of water and another molecule of water. Water has the highest cohesion of any non-metallic liquid, and you can see this if you put some water on some wax paper or some Teflon, or something where the water beads up, like some leaves of plants do it really well. It's quite cool. Since water adheres weakly to the wax paper or to the plant, but strongly to itself, the water molecules are holding those droplets together in a configuration that creates the least amount of surface area. It's this high surface tension that allows some bugs, and even I think one lizard, and also one Jesus, to be able to walk on water. The cohesive force of water does have its limits, of course. There are other substances that water quite likes to stick to. Take glass, for example. This is called adhesion, and the water is spreading out here instead of beating up because the adhesive forces between the water and the glass are stronger than the cohesive forces of the individual water molecules in the bead of water. Adhesion is attraction between two different substances, so in this case, the water molecules and the glass molecules. These properties lead to one of my favorite things about water, the fact that it can defy gravity. That really cool thing that just happened is called capillary action. And explaining it can be easily done with what we now know about cohesion and adhesion. Thanks to adhesion, the water molecules are attracted to the molecules in the straw. But as the water molecules adhere to the straw, other molecules are drawn in by cohesion, following those fellow water molecules. Thank you, cohesion. The surface tension created here causes the water to climb up the straw. And it will continue to climb until eventually gravity, pulling down on the weight of the water in the straw, overpowers the surface tension. The fact that water is a polar molecule also makes it really good at dissolving things, which we call it's a good solvent then. Scratch that. Water isn't a good solvent. It's an amazing solvent. There are more substances that can be dissolved in water than in any other liquid on Earth. And yes, that includes the strongest acid that we have ever created. These substances that dissolve in water, sugar or salt being ones that we're familiar with, are called hydrophilic. And they are hydrophilic because they are polar, and their polarity is stronger than the cohesive forces of the water. So when you get one of these polar substances in water, it's strong enough that it breaks all the little cohesive forces, all those little hydrogen bonds, and instead of hydrogen bonding to each other, the water will hydrogen bond around these polar substances. Table salt is ionic, and right now it's being separated into ions as the poles of our water molecules interact with it. But what happens when there is a molecule that cannot break the cohesive forces of water? Basically, what happens when that substance can't overcome the strong cohesive forces of water and can't get inside of the water? That's when we get what we call a hydrophobic substance, or something that is fearful of water. These molecules lack charged poles. They are non-polar and are not dissolving in water because essentially they're being pushed out of the water by water's cohesive forces. Water, we may call it the universal solvent, but that does not mean that it dissolves everything. Pretty amazing science right now. You guys are not going to believe this. Okay, you ready? It floats! Yeah, I know you're not surprised by this, but you should be, because everything else, when it's solid, is much more dense than when it's liquid, just like gases are much less dense than liquids are. But that simple characteristic of water, that its solid form floats, is one of the reasons why life on this planet, as we know it, is possible. And why is it that solid water is less dense than liquid water while everything else is the exact opposite of that? Well, you can thank your hydrogen bonds once again. So at around 32 degrees Fahrenheit, or 0 degrees Celsius if you're a scientist or from a part of the world where things make sense, water molecules start to solidify, and the hydrogen bonds in those water molecules form crystalline structures that space molecules apart more evenly, in turn making frozen water less dense than its liquid form. So in almost every circumstance, floating water ice is a really good thing. If ice were denser than water, it would freeze and then sink, and then freeze and then sink, and then freeze and then sink. So just trust me on this one, you don't want to live on a world where ice sinks. Not only would it totally wreak havoc on aquatic ecosystems, which are basically how life formed on the Earth in the first place, it would also, all the ice in the North Pole would sink, and then all of the water everywhere else would rise, and we wouldn't have any land. That would be annoying. There's one more amazing property of water that I'm forgetting. Why is it so hot in here? Heat capacity. Yes, water has a very high heat capacity, and probably that means nothing to you, but basically it means that water is really good at holding on to heat, which is why we like to put hot water bottles in our bed and cuddle with them when we're lonely. But aside from artificially warming your bed, it's also very important that it's hard to heat up and cool down the oceans significantly. They become giant heat sinks that regulate the temperature and the climate of our planet. Which is why, for example, it's so much nicer in Los Angeles, where the ocean is constantly keeping the temperatures the same, than it is in, say, Nebraska. On a smaller scale, we can see water's high heat capacity really easily and visually by putting a pot with no water in it on a stove and seeing how badly that goes. But then you put a little bit of water in it, and it takes forever to freaking boil. Oh, and if you haven't already noticed this, when water evaporates from your skin, it cools you down. Now, that's the principle behind sweating, which is an extremely effective, though somewhat embarrassing part of life. But this is an example of another incredibly cool thing about water. When my body gets hot and it sweats, that heat excites some of the water molecules on my skin to the point where they break those hydrogen bonds and they evaporate away. And when they escape, they take that heat energy with them, leaving me cooler. Lovely. Well, this wasn't exercise, though. I don't know why I'm sweating so much. It could be the spray bottle that I keep spraying myself with, or maybe it's just because this is such a high-stress enterprise, trying to teach you people things. I think I need some water, but while I'm drinking, there's a review for all of the things that we talked about today. If there are a couple things that you're not quite sure about, just go back and watch them. It's not going to take a lot of your time, and you're going to be smarter, I promise. You're going to do so well on that test you either don't or do have coming up. Okay. Bye.
So, welcome back. Hopefully Crash Course taught you the same things that I would have in our notes. If you want to go through and read the section in our notes, I think you'll see that the information he shared really matches exactly what you need to know. So let's quickly review what we've learned. So this is a great time for you to pause the video and see if you can answer these questions on your own. Great. Let's see if we can answer these questions together. Number 1, the most abundant molecule in living organisms is water. No surprise there. Number 2, substances that are water-loving are called hydrophilic. The opposite of that would be hydrophobic, and I think he mentioned that. Number 3, the ability of water molecules to cling to each other is cohesion, while the ability to cling to other surfaces is adhesion. And the ability of water to absorb large amounts of heat energy without changing its temperature is a high specific heat. And that's a huge deal. It makes a big difference in our body, in maintaining body temperature. When we talked about homeostasis, this high specific heat capacity of water really helps us to stay alive. And number 5, compounds that form ions when put into water are called electrolytes. I don't know if he mentioned that or not, but it is in your notes, and we're going to be talking more about electrolytes as we move forward into acids and bases. So acids and bases are acids right here, are substances that release hydrogen ions, also called protons. And bases are substances that release hydroxide ions or accept hydrogen ions. So they can be strong or weak, and it depends on how many hydrogen ions or hydroxide ions they are contributing. All right, on this slide, we're going to talk a little bit about salts. Another one of our objectives was to learn about salts. So here it is. A salt is an electrolyte, or an ionic compound, formed when an acid and a base are combined, and water also is formed. So here I have hydrochloric acid plus sodium hydroxide, and we get sodium chloride, NaCl, that's table salt. You guys are familiar with that, and water. So an electrolyte is a substance that releases ions when put into water, and it will conduct a current. And it says the balance of electrolytes affects the functioning of vital organs. You guys might be familiar with the term electrolyte when you're thinking about some kind of a sports drink like Gatorade. They always advertise that they provide electrolytes for you, which they do, but they also have a lot of other things you don't necessarily need, like extra sugars and things like that. So you could get electrolytes that you would need from the food that you would eat if you were having a healthy diet. All right. Number 3, pH scale. The sort of last thing that we need to discuss is the pH scale. And so pH 7 is neutral. If it is above 7, it's a base. If it's below 7, it is an acid. And hopefully you remember this from your chemistry class. Here is a picture of the pH scale. It just kind of gives you some examples of what you are going to notice. And tomorrow in the computer lab, we're going to be working on a lab simulation that talks about pH scale. So you'll be seeing several of these things in that lab. All right, and the last thing, pH of body fluids. So our normal pH of blood is 7.4, and we would have acidosis if the pH is less than 7.35. So that is a very narrow acceptable range there. We talked about homeostasis and a range of acceptable values. For blood, it's only between 7.35 and 7.45. You have to keep it within that range, so it's pretty narrow acceptable value. And so how does your body do that? It says respiratory and urinary systems work to maintain pH balance. That's true, but really what we're looking for here is buffers. Buffers help us because they can take up extra hydrogen or hydroxide ions to prevent drastic pH changes. So we can use buffers in our body. Well, I don't think, gosh, I need a buffer. Your body does it on its own to be able to assist you in that way. So here is an example of how your blood uses a bicarbonate and carbonic acid buffer system. So extra hydrogen ions, so that's acid. If we have too much acid, it will bond to form this bicarbonate. And then if we have excess OH, that's base, it can, see that ion right here, H2CO3? Oh, look, it's right there. If you get too much base, it bonds with that, and then HCO3. So you can see then we have the HCO3 ion available in our blood, which could bond with excess hydrogen. So this would be back and forth, creating an equilibrium that's going to help our blood maintain that correct pH. All right, we are almost done. So pause the video, answer these questions. Last one. Welcome back. So our answers for these questions, number 1, a substance that dissociates in water releasing hydrogen ions is an acid. Number 2, a substance that can take up hydrogen ions or release hydroxide ions in water is a base. A pH of 5.5 would be considered an acid. 7.0 is neutral. And chemicals that help keep body fluids within a normal pH range are called a buffer. And that is the end. So you're finished with the video. If you have extra time at the end of class, go ahead and go back and review your notes. All of these things are on your quiz on Thursday. It's a day earlier than usual, so make sure that you're taking the time each day to study just a little so you're prepared when Thursday rolls around. Tomorrow we'll be meeting in the computer lab to do our activity on pH, and I'll see you then. Goodbye.